To explore the concept of errors and power a little bit more, we're going to use an applet from our textbook. So I'm just going to go ahead and go to the Art of Stat webpage. And go down to their web apps. And the one that I want to use is called Errors and Power. There's a lot. Okay, so let's look at this scenario and get the applet set up. A pharmaceutical company is testing a new version of a drug that they hope will cause fewer side effects. Records show that 40% of patients experience nausea while taking the old version of the drug. The company wants to test whether the proportion who experience nausea while taking the new drug is less than 0.4. So our null hypothesis is that the new drug is just the same as the old one, so the proportion would still be 0.4. The alternative, the thing that we're trying to prove, is that the new drug is better, that it's less likely to cause side effects, so less than 0.4. So in the applet, I'm going to set my null hypothesis value here as 0.4. My alternative hypothesis is going to be less than. And let's go back to the scenario to get the rest of the details. The researchers consider a difference of 0.1 to be practically important. So if the new drug reduces the percentage who experience nausea to 30%, they want to be able to detect it. Initially, they planned a study with 50 subjects and a significance level of alpha equals 0.1. So I've already got my null hypothesis showing here in red. I'm going to adjust my alternative hypothesis. So I'm going to move the alternative down here to 0.3. So we don't know what the real effect size is, right? If we knew that, we wouldn't have to be doing this study in the first place. But we can at least say from the beginning how large of an effect would be meaningful to us. What would be a practically important effect size? So these researchers were saying that if the drug really does reduce the amount who experience nausea to 0.3, they want to be able to detect it. So we're going to go from there. We're going to say, okay, what if the effect size were really, the difference between 0.4 and 0.3? What if it were really an effect size of 0.1? How likely would we be to detect that? And let's think about what these smooth curves are actually showing us. The red curve would be showing us all the values of the sample proportion that we would expect to get if the null hypothesis were actually true. So some of them are larger than 0.4 and some of them are smaller, but that's where we're centered, because if the true value was really 0.4, then we would expect our sample values, our sample proportions, to be centered around that. The blue curve is showing us what values would we expect to get if the alternative was true. And specifically this alternative we've set where we're saying what if the new drug actually reduces those who experience nausea down to 30%, right? If that were the true value, well, sometimes it would be a little bit higher in the sample and sometimes it would be a little bit lower, but it would be centered around 0.3. And you can see there's a lot of overlap in these distributions. So at the moment, before we even look at anything, you might guess that it's going to be kind of hard to tell them apart, right? If you just see a sample proportion, it might be hard to tell whether the null hypothesis is true or the alternative. And everything else is already set up appropriately. We've got a sample size of 50 and an alpha of 0.1. So this applet lets you display type 1 error, type 2 error, and power. So let's start off with type 1 error. So notice that this is only shading under the red graph because type 1 error is defined in the situation where the null hypothesis is actually true, right? And we've set this cutoff here at the bottom 5%. So we can actually show the critical values down here. And this green line is the cutoff point, right? You can see that it's 5% on the tail, and then we've got this cutoff point. So basically anything that's below that point, we would reject the null. Everything that's above that point, we would not reject the null. So this red area here, it's under the null hypothesis. So it's saying if the null hypothesis was true, but its values to the left of the line. So this is cases where you rejected the null hypothesis when the null hypothesis was actually true. So this could happen. The cases where it would happen is if you just happen to get a sample proportion that was kind of on the low end, right? The null was actually true, but your sample proportion happened to fall kind of below what you would have expected. And in context, this would mean concluding that there was less nausea, that the new drug was actually better, when in reality the null was true, meaning that the two drugs were actually the same. Now let's add type 2 error to our picture. So type 2 error is when we do not reject the null when the null hypothesis is actually false, or the alternative hypothesis is actually true. So notice now we're shading under the blue curve because this is defined assuming that the alternative is true, that the new drug really is better than the old one, but we just ended up with a sample proportion that wasn't small enough to prove it. Even when the alternative hypothesis is true, sometimes you get sample proportions that are kind of on the large side, not big enough to draw a conclusion. And unfortunately, this is happening a lot with the plan for this original study. So this was like 59%. So even if the true value were actually 0.3, we would fail to reject more often than not. So that's not good, right? You would be coming to the wrong conclusion more often than not in this scenario. And then what about power? So power is shown here in green. So power is also defined under the assumption that the alternative hypothesis is true, right? That the new drug really is better than the old one. But in this case, we're on the left side of the cutoff line. So this means that the new drug really was better than the old one, and that your sample proportion who experienced nausea was small enough to be convincing to you, right? It was small enough to be past that cutoff line. So again, unfortunately, this is really low, 41%. Notice type 1 error and power add up to 100%. That's always going to be the case because they're both defined under the condition that the alternative hypothesis is true, and they're opposites of each other. So right now, with the study plan that we have at the moment, power is way too low. You don't want to go through the effort of carrying out a study if, a real effect of 0.1, which is the effect size you said you cared about, if you would only have a 41% chance of detecting that, right? Your power is just too low. In the next activity, you're going to see different ways that you can change the effect size, the sample size, and the significance level alpha, and see how that affects your power.